Right, this is a review for the test. This is only a summary of the material, and I will give just representative examples. It's not necessarily a complete account of what will be on the test. Okay, first of all, we'll look at the structure and nomenclature of alkenes and alkynes. Alkenes contain sp2 hybridized carbons, and the approximate bond angles around alkene carbons is about 120 degrees. You can recognize the names of alkenes because they'll end in ene. Right, so here I have 2, 3, 4, 5, 6. That would be hexene. And we want to give our double bond the lowest possible number. So we would start from this side. So this would be 2-hexene. If there are other substituents, alkyl substituents, the double bond takes priority over those. And so this would be 5,5-dimethyl. 2-hexene, and the other substituents would fall where they may. Alkynes alkynes consist of sp hybridized carbon atoms, and they have a linear geometry. Bond angles are 180 degrees. So this is 1, 2, 3, 4, 5, 6. Again, this is 6 carbons. And we need to locate the position of the triple bond. So this would be 3-hexene. Okay. And alkyne will end in yne instead of ene. Alkenes and alkynes take precedence over alkyl substituents and halogens, and also ethers, but not alcohols. Right, if we have a cyclic alkene, and here I've got alkyl substituents. I've got an ethyl and an isopropyl. Okay, we assume that the double bond is between carbons 1 and 2. Right, so this would be 1, 2, 3, 4, 5, 6, 7. Okay, this is a 7-membered ring. So this would be cycloheptene. And it would be 4-ethyl. Six isopropyl. Okay, again, it's implied, it's understood that the double bond is between carbons 1 and 2. Right, now, let's look at geometric isomerism next. Okay, not all alkenes will exhibit geometric isomerism. and alkynes will not because of their linear geometry. Okay, so this is 1, 2, 3, 4, 5, 6, 7. So this is 3-heptene. And okay, because of the trigonoplanar geometry, okay, it's implied that there's hydrogens at these positions. And so this would be cis 3-heptene. Okay, in order to make the trans isomer, okay, all I would need to do is switch two substituents on one side. Okay, for example, I could switch the hydrogen and the ethyl here. So I bring the ethyl down here and the hydrogen here, and this would be the trans. Okay, there's also the E and Z method of distinguishing between geometric isomers. Okay, so what we do here is we'll compare these two substituents. We compare the first atom. That's a carbon. Okay, we have a tie, so we need to go out to the next one. Next one out is a hydrogen here. Next one out is an oxygen. So this one has higher priority. Okay, on this side, it's a carbon versus a hydrogen. So carbon has a higher priority than the hydrogen. Okay, both substituents are on the same side, so this is the Z isomer. Let me take a slightly different example here. Okay, carbon and carbon are the same, oxygen and oxygen are the same, but for the double bond, we count that as though it were two oxygens. Okay, so the ketone up on top would take priority in this case. So we base priorities on atomic number. In case there's a tie between the first atoms, then we go out and we compare the second atoms and the third atoms and so on, until we find a difference. In this chapter, we also talked about the unique acidity of terminal alkynes. This has what's called an acetylenic hydrogen, and it is unusual for hydrocarbons to have this high of an acidity. The pKa is about 25. All right, the pKa of water, 15.7. Okay, the spontaneous direction of any acid-base reaction is always from stronger to weaker. So that means that, okay, we talked about this being acidic, but it's not acidic enough where something like hydroxide could remove it. Ammonia, though, has a pKa of about 38. So we can take the conjugate base of ammonia, NaNH2, and in this case, NH2 is able to remove that hydrogen. So we form this acetylide ion. When NH2 minus picks up a hydrogen, it becomes ammonia. Okay, so this works. Hydroxide would not work because we'd be trying to produce a stronger acid from a weaker one. Okay, it turns out this reaction is very useful in lengthening carbon chains. Okay, next we'll look at reactions of alkenes and alkynes, where we start with an alkene or an alkyne and we convert it to some other functional group. Okay, these are generally addition reactions, with the exception of the acid-base reaction that I just showed you. In other words, there's a decrease in the bond order. I introduced two terms here. One was regioselectivity. Okay, this means a particular positional isomer is formed in preference to any others. An example of that was Markovnikov's rule, where if we add an unsymmetric hydrogen acid to an alkene, the side that has the most hydrogens gets the hydrogen. The rich get richer when it comes to hydrogen. Okay, so a particular positional isomer is formed. We'll talk about a couple of reactions that are stereoselective. Stereoselectivity, a particular stereoisomer is formed in preference to another. Okay, so we'll start off with hydrohalogenation. Okay, so here we have an unsymmetric alkene, and we can add, say, HBr to it. Okay, carbon number 1, this would be 2-methyl 1-butene. Carbon number 1 has 2 hydrogens, carbon number 2 has 0. So the rich get richer. The way we draw this mechanism, the alkene group is electron rich. The hydrogen on HBr has a high positive charge, that is, it's electron lacking. Okay, we push this pair of electrons onto the bromine. Okay, and by adding hydrogen to carbon number 1, that gives us a tertiary carbocation on carbon number 2. Okay, the electrons move toward bromine. Bromine is electrons are negative, so bromide would have a minus charge. Opposite charges attract. We always go negative to positive. Our product would be 2-bromo, 2-methyl butane. Addition reactions, in particular particular, hydrohalogenation and hydration reactions are prone to rearrangement because they go through a carbocation intermediate. Okay, so for example, let's add HCl to this one. Okay, so the alkene picks up hydrogen, rich get richer, so hydrogen would go to carbon number 1. This gives us a secondary carbocation, which is more stable than what we would get if hydrogen went to carbon number 2. But in this case, we'll have a methyl shift. Okay, so this methyl will shift. Okay, so that takes us from a secondary to a tertiary carbocation. Okay, then Cl minus comes in, and we get a product that has a rearranged skeleton. All right, next we'll look at hydration, acid catalyzed hydration. Hydration produces a functional group of the alcohol. Again, I'll start with 1-butene. Water is not acidic enough to add to a double bond, so this does require an acid catalyst, and this is usually done by mixing a strong acid such as sulfuric acid with water, and that produces hydronium ions. So this is acid solution, but we haven't specified which acid we're using. It's some strong acid. All right, hydronium is a lot more acidic than water, so it's a hydronium that gets attacked. Okay, rich get richer. Hydrogen goes to carbon number 1, plus charge goes to number 2. Okay, we used up a pair of electrons, so we have an empty spot here. And then water attacks. This gives us this species called an oxonium ion. This is done in excess water. Okay, and this produces an alcohol. This would be 2-butanol, and it regenerates the hydronium ion. Okay, hydration, acid catalyzed hydration follows Markovnikov's rule, and the carbocation is prone to rearrangement, so that rearrangements are possible. Okay, I gave you an example where we didn't have a rearrangement. The most common types of rearrangements are hydride shift and a methyl shift. Okay, and these are likely to happen if we can produce a more stable carbocation. Okay, next we'll look at halogenation. This can be done with either chlorine or bromine. This reaction is stereoselective. Okay, so I'm going to start out with cyclopentene. And we'll add bromine. alkene will attack one of the bromines. Bromine attacks the other side, and then we kick out the Br minus. Right, this gives us a three-membered ring when this happens. Right, and because of this, Br minus attacks from the back side, from behind the board. And it could attack, in this case, either side. So it attacks from behind and breaks this bond. Okay, nothing happens to this bond, so that bromine is still facing forward. And then this bromine comes in from behind, so that's going to push the hydrogen forward. Okay, so we only get the trans. And that's why we say this is stereo selective. And it's trans because of this particular intermediate. Okay, this will also work with chlorine. It could work with iodine, although that usually requires heat and it's a much slower reaction. All right, next we'll look at what is called hydroboration oxidation. Hydroboration oxidation. Okay, this is both regioselective and stereoselective. This time I'm going to start with 1-methylcyclopentene. And the key thing to look for here is boron. So if you see BH3THF, or less commonly B2H6, diborane, followed by oxidation. Hydrogen peroxide and hydroxide. Okay, this results in an alcohol, and the alcohol has what is called the anti-Markovnikov orientation. So hydrogen would go to the side that has the fewer hydrogens, namely to carbon number 1, and OH would end up on the other position. Okay, H and OH are also added to the same side, so they're added cis to each other. So here's a methyl. Here's a hydrogen. Okay, so this is both stereo and regioselective. Okay, once again, if we use acid catalyzed hydration, we would get a different isomer. We would get this instead of the 2-methylcyclopentanol, we get the 1-methylcyclopentanol. Okay, most of these addition reactions can also be applied to alkynes. Alkynes can undergo often one or two additions of HBr or HCl, for example. Okay, let's look at hydrogenation next, or addition of hydrogen. Again, I'll use a cyclic alkene here. I use 1,2-dimethyl cyclopentene. Okay, this is a completely different mechanism from any of the others that we've looked at so far as alkenes and alkynes. This is one that occurs at the surface of a metal catalyst. Most commonly use palladium, platinum, palladium, or nickel as a catalyst, and hydrogen gas. Okay, this is mostly stereoselective. Okay, so you get mostly the cis isomer. Okay, you may get a little bit of the trans isomer, but mostly it's cis. Okay, I'm going to mention next the hydrogenation of alkynes. So here I'll take 2-butyne as an example. If I use a nickel, palladium, or platinum catalyst, okay, even if we don't use 2 equivalents of hydrogen, it's difficult to stop at just one hydrogenation. So in this reaction, this would take us all the way to the alkane. Carbons there. Okay, so 2-butyne would become butane. If we wanted to do just one hydrogenation, okay, we could do hydrogen and the Lindlar catalyst. This one is stereoselective. Both hydrogens are added to the same side, and so our product is the cis alkene. Okay, this takes place at the surface of the catalyst. The catalyst has been partially deactivated, so it's less efficient, and so it accepts just one equivalent of hydrogen. Right, next, we'll look at stereoisomerism. There's a lot of terms in this chapter. Right, chirality means handedness. If an object is chiral, it has this property of handedness. If it's achiral, that means it's not chiral. And what chiral means is that an object is distinguishable, it is non-superimposable on its mirror image. Enantiomers are non-superimposable mirror images. Okay, that's an important word, non-superimposable. We can distinguish one enantiomer from another in much the same way as we can distinguish a right glove from a left glove. Okay, we can distinguish enantiomers using the R and S system. Let me back up. A chiral, excuse me, a chiral or a chirality center is a necessary component of chirality. And we can recognize this because it will have 4 different atoms or groups attached to it. Okay, let's look at assigning R and S. Right, so this molecule would have 2 chirality centers. They are here and here. Okay, the name of this, by the way, would be 2-mercapto. Cyclo X 5-ene 1-ol. Okay, we dropped the E because the next letter is a vowel. Okay, and then as far as assigning R and S, okay, we have 2 stereocenters. Each one is independent. And we'll start with this one. The oxygen is 1, hydrogen is 4. We've got carbon and carbon, but then sulfur wins out over carbon. Okay, so this is 2, this is 3. Okay, so that's 1R. Okay, and then we assign priorities for carbon number 2. Right, sulfur is first priority. Hydrogen is last. We've got carbon, carbon. The next one out's an oxygen, so the group up at the top is higher priority. So this would go 1, 2, 3, like that. But our lowest priority group is not back, it's forward. And so we're looking at this from the wrong direction. So while it looks like it is S, it's actually R. Okay, because we're looking at it backwards. We would name this as 1R, 2R. Okay, if a thiol is the principal group, then the suffix would be thiol. In this case, it's a substituent. The alcohol has priority, so it's a mercapto. Right, the enantiomer of this would involve inverting all of the chiral centers. So the enantiomer would be 1s, 2s. This one has two diastereomers as well, and they are enantiomers of each other. And we would obtain the diastereomers by inverting one but not the other of the chiral centers. Or if you have more than 2, some of the chiral centers, but not all of them. Okay, so for example, all right, I kept this one the same, but I inverted this one, so this would be 1R, 2S. Okay, and these would be diastereomers of each other. If we have one chirality center, there are two stereoisomers that are enantiomers. If we have two chirality centers, as in the example I just showed, then there are four possible stereoisomers. 4 is the maximum number that we can have, and in this case there were 4. Okay, we can have fewer than the predicted number. Okay, each time you add a stereocenter, the number of possible stereoisomers doubled. Okay, so if we have n stereocenters, the maximum number of stereoisomers is 2 to the nth power. Right, so if we have 4 stereocenters, for example, we could have 2 to the 4th or 16 possible stereoisomers. Okay. The main reason why we may have fewer than the maximum number is if one or more of the stereoisomers contains a plane of symmetry. This is a compound called tartaric acid. Okay, in the Fisher projection, horizontal groups are forward, vertical groups are back, and this actually contains a plane of symmetry. Okay, it has 2 stereocenters, but this is achiral. And because it is achiral, it is identical to its mirror image. It does not have an enantiomer. It does have diastereomers, though. If I were to invert one but not the other, okay, this is now chiral, and we say it's optically active. And this is achiral, it's optically inactive. Optical activity, again, is a laboratory measurement that we take. There's a exact correspondence between chirality and optical activity, and achirality and optical inactivity. Okay, usually in a Fisher projection, because of the way we draw it, if we have hydrogens along the side, usually the chiral centers are backwards as far as assigning R and S. All right, so let's take a look at carbon number 2 here. Okay, oxygen is first, hydrogen is last. We have carbon and carbon. Carbon and carbon. All right, the next one out is an oxygen and a carbon. Here we also have an oxygen, but we can count this as 3 oxygens. And so the group up at the top would be second. Okay, and then this whole thing down at the bottom would be third. Okay, so we go 1, 2, 3 like that. That looks like it is counterclockwise, but we're looking at it from the wrong direction. So carbon number 2 is actually R. Okay, carbon number 3, okay, that is independent of carbon number 2, so we've got to assign priorities all over again. Okay, so this is 2R. Looking at carbon number 3, OH is 1, hydrogen is last. Okay, the group down at the bottom would take priority over the group up at the top, okay, because we have 3 oxygens versus 1. Okay, so this is 1, 2, 3. Okay, so that looks clockwise, but it's actually backwards, we're looking at it from the wrong direction. Okay, remember, horizontal groups are forward, so that means hydrogen is forward. Okay, so this would be 3s, 2r3s. Okay, and then this diastereomer, I've just inverted one chiral center on carbon number 3, so this would be 2r, 3r. And its enantiomer would be 2s, 3s. Okay, so look for a plane of symmetry that would negate chirality. Okay, next we'll turn to haloalkanes. So this is hexane. And we would start from the left here. This is the 2,2-dibromo. And it would be 3,4,4 trichloro hexane. So we would name these substituents bromo, chloro, iodo, and then fluoro. A couple reminders about fluoro. Okay, first of all, it's F, not FL, and the spelling is F-L-U-O-R-O, fluoro substituent. Okay, we looked at 4 different mechanisms in this chapter. These were the SN1, SN2, E1, and E2. Let's look at the SN2 first. Okay, in most cases on the test, it will identify which mechanism it is. Okay, with SN1 and SN2 reactions, we'll get a variety of functional groups as products. With E1 and E2, we're going to get alkenes. Right, this is a secondary halide. It could undergo actually all 4 of the different mechanisms depending on the conditions. Use an SH minus, a sulfhydryl ion. In the SN2, there's a bond formed and a bond broken at the same time. Okay, so this chlorine is the leaving group. This whole molecule is called the substrate. This is the nucleophile, and it's a little misleading in 2 dimensions, but this will come from behind the board. It'll come this way. So we'll form a bond and we'll break a bond at the same time. That will push the hydrogen forward. And so we'll end up with complete inversion, since this was a chiral center. Okay, so this is the S isomer, and our product will be R. Okay, so we have complete inversion. Okay, this is a good nucleophile. We have a good leaving group. This is second order kinetics. Okay, so the rate law depends on both the concentration of the nucleophile and the substrate. It's first order in both of those. The order of reactivity, methyl substrates are the best, then primary, then secondary. Right, SN2 reactions will take place faster in what is called an aprotic solvent. Some examples of protic solvents: water, alcohols such as methanol and ethanol, these usually have something like an OH, so they can accept and donate hydrogen bonds. Examples of aprotic solvents include acetone, ethyl ether, this one called DMSO, stands for dimethyl sulfoxide. Dimethyl sulfoxide. And then another common one is called DMF. Okay, these are polar, but they lack an OH bond, so they can't donate hydrogen bonds, although they can accept hydrogen bonds. Okay, so the point here is that SN2 reactions will occur, they'll occur in protic solvents, but they'll occur faster in aprotic solvents. In an SN1 reaction, this is the reaction that my lab is going to be doing tomorrow, Thursday. This takes place in 3 steps. Okay, the first step is an acid-base reaction, which is rapid. And we need to do that acid-base reaction because OH minus is actually a 4-leaving group. Okay, so we have an acid-base reaction that occurs first. Then we have what is called heterolysis, where water leaves. Okay, and this is the slow rate determining step. Gives us a carbocation. All right, we produce chloride ion in this step. Chloride can come in, and the product here is tert-butyl chloride or 2-chloro-2-methyl propane. So both these steps are fast. The heterolysis, or the leaf group leaves, is the slow rate determining step. All right, this is a first order reaction because in the rate determining step, there's only one molecule that is involved. It's a unimolecular reaction. It does not depend on the concentration of nucleophile, only on the concentration of the substrate. Right, because of the need to separate ions, this takes place best in a polar protic solvent such as water or an alcohol. E1 competes with SN1. E stands for elimination. And remember, elimination will give you an alkene. So let's look at that same reaction. Starts out the same. The second step is the same. We have the slow heterolysis step. And then this water just left takes a beta hydrogen. Okay, so it removes that hydrogen. This pair of electrons then moves to form the double bond. We get an alkene. Okay, this can occur in combination with an SN1. The major experimental factor is a higher temperature is going to promote the elimination. So if we want mostly substitution, we want to keep our temperature down. But if more than one alkene could be formed, for example, use water and heat. Okay, we have beta hydrogens here and here. Okay, we don't want to take this hydrogen. That's what's called an alpha. Okay, when more than one alkene could be formed, Zaitsev's rule predicts that the more substituted alkenes would predominate. Okay, we would also get the cis. The trans would predominate over the cis. Right, the order of reactivity for SN1 as far as substrate is tertiary, then the secondary, and primary and methyl substrates won't undergo SN1. Okay, the carbocation is too unstable. Tertiary substrates won't undergo SN2 because they're too crowded for a nucleophile to attack from behind. Okay, this is actually the same order for E1. Okay, tertiary is the fastest and then secondary. Right, let's look at E2 next. Okay, in an E2, all the steps happen at once. Okay, so this is just one step, there's no intermediate. This requires a strong base. So let's take something like hydroxide. Okay, we could get some SN2, but at a higher temperature, E2 is much more likely. Okay, again, we're going to remove a beta hydrogen, a hydrogen on the next carbon over. This one has very strict stereochemical requirements. The beta hydrogen and the leaving group have to be anti to each other. They have to be 180 degrees, so that means our hydroxide will take this hydrogen, not this one. So we remove the hydrogen, we form the double bond, we kick out the bromine, all in one step. Okay, so our product would be cyclopentene. Okay, bromine is now gone. It's a bromide ion. Right, this will also follow Zaitsev's rule unless stereochemical requirements prohibit it. Okay, so for example, if this, we're not going to form the double bond here because there's no beta hydrogen anti, so it'll have to take this one up here. And in this case, we would form our double bond over here. The order of reactivity for E2 is also tertiary, then secondary, and we can also do primary. It's a little more difficult, but it can be done. Okay, so this is the order of reactivity for E2. E2 requires a strong base. Once again, E1 would use a weak base such as water or methanol or ethanol. Oftentimes it's also the solvent that we're using. All right, next we're going to look at alcohols, ethers, and thiols. Alcohols will end in OL. Right, they take priority over alkenes and alkynes, and also thiols and ethers. So this is 2, 3, 4, 5, 6. So this is hexanol, and 3-hexanol indicates the position of the alcohol group, and the other substituents will fall where they may. So this would be 5,5-dimethyl. Hexanol. Right, if we have 2 alcohol groups, this. It would be pentane 2,3-diol. Okay, we could also call it 2,3-pentane-diol. Okay, your textbook relies primarily on the older method. This is the newer method. Okay, so a diol means you have two alcohols. A triol, in a triol you'd have three. Right. Alcohols are weak acids. Okay, most of them are about the same acidity as water, pretty close. Most of them are a little bit less acidic than water. Take something like tert-butyl alcohol or 2-methyl-2-propanol in the IUPAC. Okay, its pKa is about 18. Water's 15.7, so this is a weaker acid than water. So hydroxide wouldn't work very well as far as forming the conjugate base. Okay, one method that is often used to produce a conjugate base is to use an active metal such as sodium or potassium. There's no charge on this. This is the pure element. So this produces the conjugate base. Potassium loses an electron, hydrogen gains an electron to become hydrogen gas. All right, this is now a very useful reagent. We can use it in SN2 reactions, for example, to make ethers. This could also be used in E2 reactions to make alkenes. We can convert alcohols to alkyl halides, for example. Okay, I'm going to go ahead and draw up the complete mechanism. We start off with 1-butanol or N-butyl alcohol using HBr. Then Br minus comes in from behind. So this is an acid-base reaction. The second is an SN2. Okay, so we can make 1-bromobutane that way using HBr. This doesn't work as well with HCl. It's with a primary alcohol anyway. HCl is a little bit weaker acid than HBr, and Cl is not as good a nucleophile as Br. Okay, this takes a long time. It requires a high temperature. It's a slow reaction, but it can be done. All right, tertiary alcohols can be easily converted to alkyl halides. For example, with HCl. Yeah, I showed you this mechanism a few minutes ago. You make terpyl chloride from terpyl alcohol. Okay, a really good way of converting alcohols to alkyl chlorides is to use this reagent called thionyl chloride. And this works very well. Okay, we get good yields. The byproducts here are gases, so they can be easily removed, and of course that keeps the reaction from going backwards. Okay, a few minutes ago I talked about hydration. Next I'm going to talk about dehydration. And using cyclohexanol. Okay, we'd use a concentrated acid like sulfuric or phosphoric acid. This is an E1, an E1 mechanism. Right, the first step is an acid-base reaction. Slow rate determining step is the heterolysis, where water leaves. Okay, then we remove a beta hydrogen. Okay, and this gives us an alkene. Okay, more than one alkene could be formed. Zaitsev's rule helps us to predict the major and minor products. Okay, the more substituted alkene would be favored. All right, next we're going to look at oxidation of alcohols. Right, if we have a primary alcohol, such as 1-propanol, okay, using chromic acid, okay, this takes it all the way to corresponding carboxylic acid. If we only wanted to go to the aldehyde stage, you notice the difference here between the carboxylic acid and the aldehyde. We could use a reagent called PCC, and we do this in dichloromethane. Okay, that stops at the aldehyde. Chromic acid and many other oxidizers will take it to the carboxylic acid. Okay, for a secondary alcohol, such as, say, cyclohexanol, this is a secondary alcohol. Under both these conditions, we get the ketone. Right, a tertiary alcohol is not oxidized under these conditions. Okay, there's no reaction with the tertiary alcohol. Okay, next we'll look at ethers. common nomenclature, we would call this dipropyl ether. In the IUPAC, we look for the longest chain, which would be propane, and this would be 1-propoxy propane. Here we have both an alcohol and an ether. The alcohol takes priority. So we have 7 carbons. The alcohol is on number 2. So this is 2-heptanol. And this group on number 5, this would be an ethoxy, not ethyloxy, but ethoxy. 5-ethoxy 2-heptanol. Ethers are very flammable, but otherwise they're pretty unreactive over a variety of different conditions, and so they make really good solvents even for very reactive reagents. The main exception would be if we had a strained ring, okay, what we call an epoxide. Okay, in this case, because of ring strain, this is more reactive because it undergoes reactions in which the ring opens up. Epoxides are usually formed from alkenes. Okay, so here we have cis-2-butene, and what we use is a peroxy acid. Stereochemistry is preserved, so this is stereoselective. Okay, we start out cis, and then the 2 methyl groups are still cis in the product. Okay, and then finally we looked at thiols. This is one of the skunk compounds. This is butene, 1-thiol. We had this one similar to this a few minutes ago. Alcohol takes priority over the thiol group, so this would be 2-mercapto-cyclohexanol. Right. Thiols are more acidic than alcohols. Okay, this thiol group such as this, for a thiol group such as this, the SH has a pKa of about 10. Okay, and again, water is 15.7, so we could easily remove this hydrogen with a hydroxide. Okay, the SH doesn't leave, we just pull off that hydrogen. Okay, and then this makes a good nucleophile for SN2 reactions. Okay, we can use this in SN2 reaction, okay, such as chloropropane. Okay, this would do an SN2. Okay, and this would be called dipropyl sulfide. And then finally, we looked at disulfide formation. If we use a mild oxidizer, we can obtain a disulfide. Okay, in contrast to peroxides, in which the general formula is ROOR, which are not stable, these are stable. And disulfide formation is important to the structure of many proteins, and the fact that this is reversible means that we can change the shape of proteins, for example, and we can restore their shape in some cases. Right, so that is all for our review. I'm going to go ahead and end this meeting.